stream. Almost as if you've done this several times already, and it's been totally fine. In fact, your community is unusually supportive of even the streams that don't go so well. True. One thing that's different from this stream than from previous streams is how I have a second monitor now. Hi! Thank you for coming and watching me, despite the warnings of the title that the stream might not be so great. But thank you, I appreciate it lots. Welcome to the chat, Virgil. I don't quite understand why your username shows up as Virgil for your first message, and then shows up as something else for the second message. Unless you're two different people. No, that doesn't work. Anyways, thank you for coming and watching. Mwah! Masked autoencoders are scalable vision learners. Autoencoders are neural networks which you train by just testing them to see if they output the same as their input, but they don't have enough parameters to properly represent the input image, and thus they can't just memorize each input image. Thus they hopefully understand the abstract concepts of the input somehow. This paper shows masked autoencoders are scalable self-supervised learners. Self-supervised is the term for... I really appreciate how I announce that, hey, I'm going to do a bad stream, and then you come and watch anyway! So self-supervised in computer learning means that we don't have to have a human go around and manually say what the correct answers are. Somehow the computer figures out what the correct answer is during the learning process. Usually this means we construct a task that we already inherently have the answer for. Like, for example, autoencoders which map an object to itself, and then we have a way of manipulating that. I really appreciate it. So generally we have a task that inherently has its answers, and then we are able to do something. Oh right, then we manipulate that somehow, and we get an actual computer that learning model that does something interesting. First, we develop an asymmetric encoder-decoder architecture where the coder operates only on the visible subset of patches without the masked tokens, along with a lightweight decoder that reconstructs the original image from the latent representation and the masked tokens. Latent representation meaning the model's internal brain ideas, if we're using a brain analogy. Second, we find that masking a high proportion of the image yields a non-trivial and meaningful self-supervatory task. Coupling these two designs enables us to train large models efficiently and effectively. We are self-training by 3x or more and improve accuracy. Our scalable approach allows for learning high-capacity models that generalize well. Example, a vanilla VT huge model achieves the best accuracy, 87.8% among the methods using only ImageNet-K data. Transfer performance and downstream tasks. Outperform supervised pre-training, shows promising scaling behavior. So that sentence I think means transfer performance means the ability of the model when we're using it to do something actually useful. Array architecture. So you see we have a image that we mask and then we send it into the decoder. We encode it into a bunch of numbers. And then the decoder turns that back into the original image. And then the model is rewarded or punished. Kind of, not really. The model learns, trying to minimize the difference between this image and that image, according to the areas which are not masked. During pre-training, a large random subset of image patches, i.e. 75%, is masked out. Is that really 75%? 1, 2, 3, 4, 5, 6, 7, 8. Yeah, this is for tracking software. So what I was doing is I was reading a different paper, namely, one about face normalization. So, yeah, oh no, yeah, for face normalization, namely, this paper is about a piece of software that turns random faces all into the same guy who has the expression of the corresponding face. As we can see, the sad man becomes a generic sad man, and the surprised baby becomes a surprised man. And this is useful because you want the tracking software to perform equally well on all different people's faces. Like, I don't want to make a tracking software that only works on me. And down here, as I was reading the paper, and they referenced this paper that I was reading at the start of the stream. They specifically employ a pre-trained masked autoencoder to extract the facial features. And thus I want to learn about masked autoencoders, because if I can teach the software to understand parts of human faces, then we can get it to understand eyes and such. And this is a technique that has risen post. Let me open up the Discord and read what it is I said yesterday. Oh, this technique, I believe, was invented after OpenSeeFace, which is what lots of VTubing software uses for tracking right now. And thus, if I use more modern techniques, maybe I can get better performance. maybe there's a trade-off between me using better techniques and me not knowing what I'm doing. But either way, I can almost certainly outperform the technique which I'm using right now in my new software, and also in this software, but it's a different technique in this software, which are just example networks that are bundled with the corresponding machine learning libraries to just be like, oh, want to test out the machine learning library? Here's a little thing you can easily do, rather than being something that's actually for production use. I'd say that. I don't know why I said it. I started that sentence so confidently, hoping that I'd have something sensible to say by the time I got to the end of it. However, I did not. What were we reading? I was continuing so well. Oh, I went directly. Oops, that was a mistake. Reading 2-column. I want to try out something. Try out reading, but only if I could figure out something like voice to TTS. Well, the good news is that unusually good. There's been lots of progress in both voice to TTS, specifically, OpenAI Whisper came out recently, which means the open source model, the free open source model, are now significantly better than they used to be. It's kind of surprising that we don't have good voice changers, because we have so much progress in other fields of machine learning, or what broadly gets called AI these days. But for whatever reason, voice changers are still rubbish. The idea of VTuber speaking with like a Hatsumiku style voice does seem appealing to me, because then you've completely gotten rid of any human element to it. There is downsides in that it doesn't capture the emotion as well, but you can like really ham up the body acting, particularly if you have like full body tracking. This is what Zendaya, I believe her name is Zendaya of. Yeah, so the problem is that voice changes just sound bad right now. I don't know why. Maybe no academics or no big companies have really focused on it. I'm currently very busy. Or busy in that I'm focusing on my VTuber software, so I don't have time to also learn how to make a voice changer. But maybe one day. Maybe. Definitely no promises, though. Oh, Zendaya! Zendaya. This is the only VTuber I know of that uses an artificial voice with text to speech. One of the jokes on her channel His chat tricks her into saying a phrase that text-to-speech picks up as different words, and thus she says different words than she was intending to. Deep learning has witnessed an explosion in architectures of continually rapid growing capability and capacity aided by the rapid gains in hardware. Models today can easily overfit 1 million images. Oh wow! Begin to demand hundreds of millions, often publicly accessible labeled images. This appetite for data successfully has been successfully addressed in natural language processing by self-supervised pre-training solutions based on autoregressive modeling in GPT and masked autoencoding in BERT. Are conceptually simple. They remove a portion of the data and learn to predict the removed content. These methods are now in. So that's how this paper is from December of 21. So GPT and BERT are what have evolved to go on to power things like ChatGPT. Masked autoencoders, a form of more general denoising autoencoders, is natural and applicable in computer vision as well. Indeed, closely related research in vision preceded BERT. However, despite the significant interest in this idea of following the success in BERT, progress of autoencoding methods in vision lags behind NLP. We ask, what makes autoencoding different between vision and language? We attempt to answer this question from the following perspectives. Until recently, architectures were different. In vision, convolutional neural networks were dominant for the last decade. Convolutions typically operate on regular grids, so it's not straightforward to integrate indicators such as mask tokens or positional embeddings to convolutional networks. This architectural gap, however, has been addressed by the introduction of vision transformers. Woo! You see, I don't know what vision transformers are. Thus, maybe I will learn a little bit. Or not today. I shall make a new tab dedicated to that. And then just checking my memory consumption. Also because I realized I left open. Oh good, I did close my tabs all properly. So I'm not wasting a bunch of memory with a bunch of YouTube tabs. Convolutions typically operate on regular grids. Oh no, we already read that. Information density is different between language and vision. Languages are human-generated signals that are highly semantic and information dense. When training a model to only pick a few missing words per sentence, this task appears to induce sophisticated language understanding. One of the cool things about papers is how much background information they include, so even someone like me, who doesn't really follow the literature, can tell what's going on. Images, on the contrary, are natural signals with heavy spatial redundancy, i.e. a missing patch can be copied from neighboring patches with little high-level understanding. Example results in image validation images. For each triplet, we show the mask image left, our May reconstruction middle, and the ground truth right. The masking ratio is 80%, leaving only 39 out of 196 patches. So here they have, let's zoom in. Oh, I'm not capturing my cursor. That means I can't point. Let's fix that. Oh, it does capture my cursor. Never mind. I don't know why I was mistaken on this. So we have these gray boxes where the model says, oh, we have this. Please draw the rest of the image. And then it's draw this image, which approximates this image. And it has successfully understood the concept of clocks that are circular, or at least the concept of circles. It did not deduce, for example, that there should be numbers on the clock. Oh, here it successfully reconstructed the idea of chia faces, kinda. So, like, this is pretty successful. Ooh, it pretty failed on this. We might know that this is kind of reminiscent of highly compressed video, which this kind of is. Because computer autoencoders and regression are actually pretty similar. As no losses is computed on the visible patches, the model output on visible patches is qualitatively worse. So this sounds like the model is not punished for duplicating the parts of the image that it can already see. For example, you can see this little edge here, and it reproduced them quite terribly. So internal to the model's thinking, it has thought like, aha, I can see this, therefore I know I don't need to do a good job predicting it. Because it also knows what patches it's been given. But they're saying that you could just post-fix overlay this image, these patches onto the final image if you really want to reconstruct it. If we actually cared about that. This is a different data set, Coco. Oh! Now this is interesting. So here, we can't really tell what's going on in this image because we don't see much data. So it's that, well, people are pretty common, so they probably have heads of some sort. But no, it was secretly an image of mannequins without heads. Likewise here, there's some sort of animal. I guessed a dog, but it was actually a cow. But dog is kind of plausible for it as a thing to guess. Okay, now back to the main body. We were just talking about how in images, lots of the information is redundant. So, to overcome this difference and encourage loading useful features, we show that a simple strategy works well in computer vision, masking a very high portion of random patches. This strategy largely reduces redundancy and creates challenging self-supervising tasks that require holistic understanding beyond low-level image statistics. To get a qualitative sense of our reconstruction task, see figures 2 to 4. That's what we just did. I love having two monitors. I see why streamers endorse it so much, because I can look over and make sure that I'm streaming something sensible instead of having to like switch which window is on top. The, the autoencoder's decoder, which maps latent representation back to the input, plays a different role between reconstruction, text, and images. In images, the decoder constructs pixels, hence its output is of a lower semantic level than common recognition tasks. This contrasts to language where the decoder detects missing words and that contain rich semantic information. While the BERT decoder can be trivial in machine learning language processing, we found for images the decoder design plays a key role in determining the semantic level of the learned latent representations. Oh, this is important because I want the learned latent representations to be how faces work on humans, particularly what expressions they make. I do have so one thing that frustrates me with the simple models that I've played is that if you raise one eyebrow, the model raises both eyebrows. And thus you don't actually have very much precision in the expressions you make. And that makes it... It makes it feel like you are trying to manipulate a puppet, but you're like... It's very wooden. Doesn't have the expressiveness that I would like. Now, because we don't want like a simple map for my real face onto the anime girl, because who knows what horrors you might see on my actual real face if you map it too closely. But it does mean we just have less tools to work with. For example, it could be useful to be able to raise my left eyebrow to trigger some sort of expression that my real face can't do, or at least, since of course I'm actually an anime girl, models trained on real humans can't pick up. For example, real humans don't have a way of turning their eyes into currency, and thus you won't find that in the data sets, so I won't be trained on that. Driven by this analysis, we prevent a simple, effective, scalable form of masked autoencoder for visual representation learning. Our MAE masks random patches. Oh yeah, it's a thing that takes some practice. I learned it because for a while, I had a hobby of trying to learn to move individual muscles on my face independently. I spontaneously developed the ability to raise one eyebrow. Fortunately, you can't see it, but then with practice, it's hard to describe. It's just kind of like looking in the mirror and trying to do it, or like doing a similar, like raising both eyebrows and then trying to put down the other eyebrow. And then, if you do this enough, eventually you learn to do it. At least that's how it worked for me. I've been trying to get better slowly. I have not been practicing regularly. Better at, shutting one eye without, like, winking without scrunching up my face. For one, this is useful if you're putting on makeup, because then you can still see what you're doing. Now you've also found that it leads to terrible errors. You do better if you just shut both eyes and feel about. It's true. Yeah, it's potentially useful if I can get a model that picks it or get a vision model. I keep saying model every time computer learning programs after they've been trained are called models. And thus, that shouldn't be confused with like a VTubing model, which is like a series of images that are distorted in various ways. So if I can get a model for the tracking that picks up these various movements, I could potentially use them to good purpose. They'll be asymmetric autocoder design. Our autocoder operates only on the visible subset of patches without mask tokens. And our decoder is lightweight and reconstructs the image for the latest representation along with the mask tokens, shifting the mask tokens to the small decoder in our asymmetric decoder results in a large reduction in computation. Late, but I forgot makeup exists, lol! I should do it more often. I'm bad at keeping my face still for it. Yeah, I have stabbed myself in the eye more than once while trying to apply mascara. So I've only bought the fake eyelash glue that's also eyeliner. I'm beginning to think that invisible eyelash glue is better for amateurs like me, because then it will matter less if I get it all over the place, because I struggle because I put it in the right place, and then I blink wrong, or I smudge it with my fingers as I try to put the fake eyelash on. Quite difficult. One trouble with mascara is that it only lasts a short period of time in the bottle, like 3 months or so, before you're supposed to throw it out. Either because it gets contaminated with germs, or because it gets all clumpy and thus it looks bad when you put it on. This can reduce pre-training time. Oh, if you do want to get into makeup, make sure that you buy makeup remover before putting on makeup for the first time, so that you don't have like an issue where you put on makeup poorly and then you have a hard time putting it on correctly. This can reduce overall pre-training time. Likewise, reduce memory consumption, enabling us to easily scale our made to large models. So I don't necessarily want a super high capacity model, to be honest, because I want my model to go fast. But there's also techniques for making big models smaller. Though I don't know those will map as well into... I have some only because I fail miserably every single time. Whoa! Our May learns very high capacity models that generalize well. With mal pre-training, we can train data hungry models, like with May pre-training. That's where you train some weights that go inside the model, some numbers, and then you take those numbers, you put them in a different model that does some other task. On ImageNet 1K with improved generalization performance with a vanilla 1VT huge model, we achieve 87.8% accuracy when fine-tuned on ImageNet-1K. This outperforms all previous results that only use K, the ImageNet data. We also evaluate transfer learning, object detection, instant segmentation, and semantic segmentation. I have yet to try like foundation with makeup. I don't draw them when I draw my face, but I do have like, I can see like the veins under my eyes. The foundation might make me look better by some standards, assuming we don't like the veiny look. Perhaps if I'm wanting to go to like a vampire convention, make sure the vampires are attracted to me, I might want to really embrace the veiny look, so they know I'm full of blood. The blue veins in your skin aren't blue because of the blood. They're blue because that's what the outside of the veins look like. I think the contents of the blood might matter a little bit for the color, but not, I know that's not true. It's not that the blood is literally blue because it doesn't have oxygen in it. No, that's not the reason. These observations are aligned with those witnessed in self-supervised pre-training in NPL. We hope we will enable our field to explore a similar trajectory. Beep boop 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 boop. Ooh. Deconstructions of ImageNet validation and images using made pre-trained with a masking ratio of 75 were applied on your inputs. Oh! So here the model somehow learned to generalize. Oh, if you're too veiny, they might think that you're sickly. That you might taste nasty. Oh. True. So here their model works even when it's trained on input, or so it's trained on just 75%. But here they cover up 95% of the image and can still make a reasonable guess. Like, oh, maybe there's a zebra in the image. Oh, maybe it's a mushroom. Or, oh, maybe it's a bus. Oh, maybe there's some tomatoes. Related work. This is a classic thing to do in academia, where you go around and list all the other work that's kind of vaguely related to yours. Mass language modeling. As our aggressive parts of birds and group, highly successful methods for pre-training NLP, these methods hold a portion of the input sequence and train models to predict the missing content. These models are shown to scale excellently. A large scale of evidence in case these pre-trained representations generalize well to various downstream tasks, auto-encoding. The classic method for learning representation is a classical method. Masked image encoding learns representations from images corrected by masking. That's kind of what we're doing here. The pioneering work of 59%. Masking as a noise type. Day. Denoising autoencoders. Oh, I should have read this section that I skipped earlier. Denoising autoencoders are autoencoders that corrupt input signal and learn to reconstruct the original uncorrupted signal. series of methods can be thought of as generalizing A under different corruptions, masking pixels, moving color channels. RMA is a form of denoising autoencoding but differs from classical A and numerous arrays. Masked image encoding, okay. IGBT operates a sequence of pixels, 6 unknown pixels. The VIT paper studies masked patch prediction for supervised self-learning. Most recently, BIT proposes to predict discrete tokens. Self-supervised learning approaches have significant interest in computer vision, often focusing on different pre-text tasks for pre-training. Recently, contrastive learning has been popular, which models image similarity and dissimilarity between two or more views. Contrastive and related methods depend strongly on data argumentation. You didn't read the words that were on the paper! It's true. But luckily I said the words just in the wrong order, and the meaning is preserved. Just like what an autoencoder might do. Autoencoding preserves a conceptually different direction. It exhibits different behaviors as well, as we will present. Our approach, our masked autoencoder, is a simple autoencoder approach that reconstructs the original signal given its partial observation. Like all autoencoders, our approach has an encoder that maps the observed signal to a latent representation and a decoder that reconstructs the original signal from the latent representation. Unlike classical autoencoders, we adopt asymmetric design that allows the encoder to operate only on the partial observed signal without mask tokens and a lightweight decoder signal that represents the full signal from latent representation. Unfortunately, I was thinking about something else where I read that sentence. Namely, I was thinking about a different part of thing that I'll probably want to do, which is normalizing the what way the head is pointed. Because I want to track head movements, not just expressions. And thus, if I can turn the head towards, do image editing to turn the head towards the camera before doing facial analysis, this has potential to improve things. To make it so that when you smile, turn your head, the smile still works. On the other hand, you do the easier thing and just train out a different bunch of different shapes. I think we may actually want to do that, because my current hypothesis plan is we make one of these coders that understands the human face really well, bring out a bunch of data, and then we build models that take the latent representation and try to turn that latent representation into something useful after freezing the weights. And that way, we can extract various different kinds of information. For example, we could extract head tracking, and we could extract facial key points, and what expression you're making. It'd be cool if your expressions could auto-trigger, except for you having to remember to press a key every time you feel an emotion. Likewise, be nice. Give model makers options or just nicer inputs. Like for example, I might want to make a model where I've gone through and manually tagged which muscles or which parameters the person in the image is making, and for what outputs I want for the models creators to consume, instead of having to figure out some more indirect method for trying to extract stuff. I also ideally would like my trading in that input to include video, because the thing about tracking is that we have a video because the webcam is continually running, and thus the model should be able to learn to make assumptions. For example, that if I move my head, then likely the key points have moved smoothly, and this should help with interpreting image footage rather than treating each input frame separately. For example, maybe the model should get the previous 4 frames. It has to predict the next frame from that. Following VIT, we divide our image into regular non-overlapping patches. Then we sample a subset of patches and mask, i.e. remove the remaining ones. Our sampling strategy is straightforward. We sample random patches without replacement, following a uniform distribution. We refer to this simply as random sampling. That was another sentence I read without reading. We need to scroll back. Apologies to the audience, because I would like, for the audience to not listen to me reading the same passage over and over again. The trouble is, I too want to learn. Unlike okay, so let's read this whole paragraph again. Our masked autoencoder is a simple autoencoding approach that reconstructs the original signal giving its partial observation. Like all autoencoders, our approach has autoencoder that maps the observed signal to the latent representation, the decoder that reconstructs the original signal from the latent representation. Unlike classical autoencoders, we adopt an asymmetric design that allows the encoder to operate on aha! Focus, 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 I say to myself. Like all autoencoders, our approach has an encoder that maps the observed signal to the latent representation. The decoder that... Okay, this is just what we've read before. Obviously, you've read this paragraph 3 times. Yeah, but like, it's what we understand already. Unlike classical autoencoders, we adopt an asymmetric design, which makes the encoder only works in one direction. Masking. Following VIT. Oh, that's another paper I might want to read. VIT. To see what's happening there. Following VIT, we divide an image into regular non-overlapping patches. We then sample a subset of patches and mask, i.e. remove the remaining ones. Our sampling strategy is straightforward. We sample random patches without replacement, following a uniform distribution. Random sampling a high masking ratio, i.e. the ratio of removed patches, largely eliminates redundancy, thus creating a task that cannot be easily solved by extrapolation from visible neighboring patches. The uniform distribution prevents a potential center bias. Okay, yeah. Finally, the highly sparse input creates opportunity for deciding an efficient encoder introduced next. Okay. This is the efficient encoder. Our encoder is a VIT. Okay, I definitely need to read that paper now. But applied only on visible unmasked patches, just as in a standard VIT. Our encoder embeds patches via linear projection with added positional embeddings, then processes the resulting set via a series of transformer blocks. However, our encoder only operates on a small subset, the full set. The past masked patches are removed, no masked tokens are used. This allows us to train very large encoders with only a fraction of the computer memory. The full set is handled by the lightweight decoder. Okay, so I think this means that the encoder presumably gets a series of blocks. Sometimes the blocks are just missing. I think I have to understand a VIT to be able to understand exactly what they're doing. Like 60. Transformers for image recognition at scale. Aha! Here's the paper. Download paper. Download the paper. Yay! And open the paper in my streamed browser. And we can travel over here and start reading that paper. Wada! Ha 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 ha! Currently I have 0 viewers, so either I actually have successfully found a video or a task which is sufficiently boring to stream that I've scared away my audience, or there is another task, possibility. People had to leave for various reasons unrelated to the task which I'm doing, where I am also streaming at an unusual time. Yeah, in part because you were scared of your audience, and you wanted to stream when they wouldn't show up and thus wouldn't be disappointed by the boring stream. You are not without valid cause. Image is worth 16 by 16 words. Transformers for image recognition at scale. While the transformer in architecture is the default standard for natural language. Oh, you're just speaking. Ah! You're still. Ah! 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 You're still. Ah! I really appreciate it. In this case, I can know that I can't trust my stream analytics from YouTube. I hope the baking goes well. You caught me being honest when I thought I was in private. We show this reliance on CNNs is not necessary. A pure transformer applied directly to a sequence of image packages can perform very well on image classification tasks. Oh! a pre-trained image on a large amount of data and transferred to multiple small image. When pre-trained on a large amount of image data transferred to multiple mid-sized or small image recognition benchmarks, this transformer attains excellent results compared to the state-of-the-art convolutional network. Okay. No idea why it goes down when I put it in picture-in-picture, with the stream in picture-in-picture, so that's weird. Don't worry about it. I'm not trying to win the analytics game anyway. This is not a stream that I'm doing in attempting to get famous and big. I do appreciate you guys showing up, giving me attention. My plan for getting famous and big is to have clout, is, releasing a new VTuber model. Or I should say not VTuber model, but VTuber engine. Okay, so it was more or less what I guessed it would be. Our encoder is a VIT but only applied to the... Okay, so with this, we can now understand this. As I guessed, in a VIT, they chop up the image in a bunch of small chunks, and then they only send some of the chunks over to the transformer. But presumably the transformer also knows where in the image they appear, because it's also passed that information, and thus it learns that. We're actually going to reopen... No. We're actually going to reopen the closed tab, because I want to read it later, just in case they're doing something different. Mask packages are removed. The day encoder. It's a full set of tokens consisting of encoded visible patches and the masked tokens. Okay, so this is the decoder. Oh, maybe the encoder doesn't know what's been masked. I'm not entirely sure. The decoder definitely knows what's been masked. Each mask token is a shared learned vector that indicates the presence of missing patch to be predicted. We had positional embeddings to all tokens in this set. Without this, the masked tokens would have no information about their location in the image. Oh, so this seems to confirm that the encoder does not know where the blocks are. It just sees this block and says, guess I need to encode it somehow. And then then encodes it somehow. The decoder is only used during pre-training to perform the image reconstruction task. Only the encoder is used to produce image representations for recognition. Therefore, the decoder architecture can be flexibly designed in a manner that is independent of the encoder design. We experiment with very small decoders, narrower and shallower than the encoder. For example, our default decoder has only 10% computation per token than the encoder. This asymmetrical design, the full set of tokens, are only processed by the lightweight decoder, which significantly reduces pre-training time. So I wonder if that's actually appropriate for me, because I want the latent representation to include just information about the face and not all the stuff about about the expression. No. I don't care about reconstructing the actual face or the background. I just care about reconstructing the face in the image's expression. So we'll probably want to go back and read the other paper to see what they do to remove the useless information or isolate it better. Like most things in neural networks, it will probably require some experimentation on my half. If I got really fancy, I could actually start investing money in training the networks. Though, for now I think I will stick with just making really small ones. To be what I'm currently using, it should be pretty easy. And potentially to beat the models that OpenSeeFace is using, it might also be pretty easy. Reconstruction target, or may reconstructs the input by predicting the pixel values for each masked patch. Each element in the decoder's output is a vector the pixel's values represent. Ding. A patch. The last layer of the decoder is a linear projection whose number of output channels. That was me pausing to see what. What? That was me pausing to see, something. Oh, to try and understand what linear projection is. Linear projection, that would just be what is normally called a fully connected layer, but without the nonlinear step. Our loss function computes the mean squared error between the reconstructed and original images in the pixel space. We compute the loss only on masked patches, similar to PERT. We also study a variant with a reconstructed target is normalized pixel values of each masked patch. Specifically, we compute the mean and standard deviation of the pixels in each patch and use them to maximize the patch. Using normalized pixels in our reconstruction target improves the representation quality in our experiments. Ooh! This suggests that I want to do that most likely. Simple implementation, but I should also potentially look for, if I choose to take this route, I should try to read more papers where they do the May thing to see if better stuff has been figured out, because these are the first people who tried it. And we have like 4 years of research, pretty heavy research, because AI lab investment is really heavy right now. First, we generate a token for every input patch. A linear projection with added positional embedding. Next, we randomly shuffle the list of tokens and remove the last portion of the list. Wait, what? Our May training can be implemented effectively. Importantly, does not require any specialized sparse operations. First, we generate a token for each input patch. Okay, so they have a positional embedding by linear projection with a added positional embedding. Next, we randomly shuffle the list. Randomly shuffle the list of tokens and remove the last portion of the list based on the masking ratio. This produces a small subset of tokens for the encoder. It's equivalent to sampling patches without replacement. Okay. After encoding, we append the list of masked tokens to the list of encoded patches and unshuffle the full list. to align the tokens with their targets. The decoder is applied to this full list with the positional embeddings added. Okay, so as noted, no sparse operations are needed. This implementation produces negligible overhead as shuffling and unshuffling operations are fast. Computing the loss only on masked patches differs from traditional denoising autoencoders that compute the loss of all pixels. This choice is purely result-driven. Computing loss on all pixels leads to a slight decrease in accuracy. We're switching to another scene where I actually change the settings of my browser to get the scroll option because I'm really bothered by not having autos and scrolling for moving around quickly, particularly sideways. I want settings. Open links for active tab. Search. Horizontal tabs. Contrast, control, zoom. Edge. Use auto-scrolling. Yee! We have back our glorious scroll tool. Fortunately, it does not show up on the stream, so you're unable to witness the glory what it is. Hardly glory, it's just a grey rectangle with some errors in it, and a feature with browsers have supported. From before you awoke from your slumber. At least before I woke from my slumber, and I was there when you came to, because I'm genius like that. Because I was conscious the whole time. Because I am Rex the Abomination. High masking ratio works well for both fine-tuning top and linear probing bottom. I have no idea what linear probing is. I'm going to make a new tab just searching that to see what it is I'll read about after stream. Y-axis of the internet IK validation accuracy on all plots in the paper. No. Ah! Okay. ImageNet experiments. Now we get to learn how effective it was. We do self-supervised pre-training on ImageNet IK. Image training set. We do supervised tuning to evaluate the representations with end-to-end fine-tuning or II linear probing. Oh, then we do supervised training to evaluate the representations. Okay, I actually need to be gone for a bit. I'm just been ignoring chat. We've been learning all about autoencoders, particularly these masked autoencoders, which potentially allow us to use a bunch of random images instead of having to hand label stuff to do the hard work of pre-training. However, I'll be gone for a short while because I've run out of water and I need to drink. But I'll be back soon. We have survived the adventure outside my room. So we do supervised training to evaluate the representations with end-to-end fine-tuning, linear probing. Okay, then we report top 1 validation accuracy of a single crop. I'm not sure what this means. I might have to look up what linear probing means on stream. Linear probing. Linear probing and hashing a simple lightning fast hash table implementation. This is not what we care about. So, I should pop out. Oh, okay. Yeah, I definitely should have popped out. Chat? Use my glorious screen real estate to actually benefit from this. Okay, maybe this is a stupid question. I don't think so. And maybe this is a stupid question, but how exactly would this kind of face tracking translate to vtuber expression slash movement? Does it just recognize a certain expression and toggle the corresponding face asset? So, I don't have my drawing tablet set up, but I will draw some diagrams to keep my hands busy while I'm talking. So, ah! Ah! So how it would, so what we have is we have like 3 steps. I say confidently, not knowing what those 3 steps might be. I think we might only have 2 steps. Virgil, are you talking, Chris? TV, are you watching the stream during class? Oh, well that would explain things. Oh, I can tell myself this. They aren't talking about me. They're just... Oh, whoops. Okay. So, right, Sheepy, the class is already in way much ago. Oh, good. I'm glad you're being a responsible student. Well, it may be fun and freeing for the streamer to say things like, oh, skip school, watch my stream, and I do like the glory and the ease of like saying, ignore the rules, nothing matters. I do want to be like not responsible for ruining the careers of any of my fans. This is a disadvantage I did not foresee. Namely, I can't draw arrows on top of somewhere I've already drawn, it appears. Or you can like deselect it and reselect it. I mean, I do sleep with sunglasses, so unfortunately there is a level where skipping classes is actually probably the correct thing to do. So if we have the screen and we have the display. Oh, that's what the 3 categories are. So we have your screen on the left, or we have like webcam input, and this supplies some sort of input to the model or to the vtuber software, and then the vtuber software supplies like actually drawing the image. And the question of how would this kind of face tracking translate to the VTuber expression or movement? This is up to what the VTuber software does. And potentially my VTuber software, it will depend on what's it potentially depends on how the VTuber model in the VTuber software is rigged against the various inputs. For starters, it will be things like currently my tracking extends on this model, extends in this version in Waifu Tier 1, extends this far. We have shoulder tracking, and we have nose tracking, which moves about my head. And then we have volume of my speaking, which outputs which affects how big my mouth is. So if I say quiet sounds like this, we have a relatively small sound, or if I make a loud sound, like by clapping, my mouth gets big. The baseline of matching the tracking that, say, VTuber Studio does means that if I like squint my eyes, the eyes of the model would also squint. I'd also like it such that I could squint one eye, squint the other eye, and only one eye would squint. I could shut my eyes to express this emotion instead of having to remember to press a key to have this emotion. The dream, but like triggering expressions, like for example, happy when I smile, it's okay. The shoulder tracking mostly is not useful. Mostly it causes me to bug out worse if the tracking fails on me. For example, if I do my hair in a way such that the tracking gets confused and can't find my shoulders, even the shirt I'm wearing, then I will jump across the room in the model because it thinks my shoulders are at a weird angle. So anyways, exactly what it does is determined by a later point. At this point, this paper is actually more about describing something even earlier. That's more like over here, which takes an image and encodes it to some non-human comprehensible input, and then we will make a second computer vision model, which decodes that in various parameters like head turn and expression and maybe mouth shape. think it would be neat. So, like, I've tried having hand early on in my model. I actually had very simple hand tracking. The trouble is, most of the time the hands are not in frame, and then I briefly move my hand in frame, and it lead to a weird jerk in my model. Because I'm so sorry. That is not how you pronounce that word, Sheepy. It's sorry. Yeah. I guess maybe I don't need to feel too jealous of Wemmy from Face Connect of speaking in a way where she struggles to say ours. Because apparently I do too. Sorry. I can't remember what I was saying. Oh, right. Oh, right. Sorry for breaking immersion, but like I'm actually sitting at a desk using a keyboard rather than demurely folding my hands in front of me as I stream. But anyways, if we could set it up such that it like detects moving my hands in front of my face, or like when I do make gestures, if you could pick those up in some symbolic way, that could be potentially great because I do find myself accidentally making gestures which don't get picked up. How Canadian of you? As you see, I mean, Sheafy can't be real Canadian. My greatest honor is actually that I slurped up all the real Canadianness. It's just fake Canadians from here on out. Well, at least that's what I say, and that's what Sheepy believes. What do you mean Sheepy believes? No comment. We do self-supervised pre-training on Image K1. We use VIT large as the backbone of our ablation study. Very big. Tends to overfit. So overfitting is when you have... Overfitting is when the computer vision model just memorizes everything in the database. Like says, Canadian. Ha! Cute. Ha! You're big that you're cute. No! Not that. Hmm. So very big models that have lots of parameters have the ability to just memorize everything in the data set rather than actually learning like principles of like what a cat looks like. Instead it learns, aha, these particular pixels are cats. Because what they're testing it on, what this paper is about is by a classification model, because that's kind of like the default thing where you're trying to teach a computer to identify what's inside images. Good recipe with strong regularization is needed. Even so, I may pre-training attribute contributes a big improvement. Here, fine-tuning is only 50 bucks versus 200 from scratch, implying that the fine-tuning accuracy heavily depends on the pre-training. Ooh. That means that the pre-training actually did something and wasn't just wasted cycles to get more effectively with random. There are various methods of detecting when you've trained your a model enough such that more training doesn't lead to any better results. So I presume that that's what they did here. We ablate our mal using the default settings. I'm not super confident what ablate means. Also, I didn't lower the linear probing mount either. According to Wikipedia, ablation is the removal of a component from a system. An ablation study tries to determine the contribution of a component to an AI system by removing the contribution, then analyzing the resultant performance of the system. This is from Wikipedia, the free encyclopedia that anyone can edit. We ablate my by using the default settings, table 1. Masking ratio. I'm super confident what they mean here. Maybe they can mean, but maybe we'll figure out once we get to table 1. Because it does have a caption, or so the rumor goes. The ratio of 75 is good for both linear probing and fine-tuning. This behavior isn't kind of the typical masking ratio is around 15. Our masking ratios are much higher than those of related works in computer vision. The model infers missing patches to produce different yet plausible outputs. It makes sense of the gestalt of the objects in the scene, which cannot simply be completing extending lines or textures. We hypothesize this freezing-like behavior is linked to the use of useful representations. No! We lost our place. Oh, luckily! Finding our place again wasn't so bad. Figure 5 shows that linear probing and fine-tuning results follow different trends. For linear probing, the actually increases steadily with the masking ratio until a sweet point. The accuracy gap is up to 20%. 57 versus 75 with fine-tuning. Ratios are less sensitive to the ratios and a wide range of masking ratios work well. 40 to 80. Okay, so this is table 1. May ablation experiments. Deep decoder can improve linear probe accuracy. Decoder width. The decoder can be narrower than the narrower than the encoder. Mask tokens. The encoder without mask tokens is more accurate and faster. This is unsurprising. But that's potentially good. I'm not super confident if that means if they don't do any masking at all, or if they mean after training. I think if this is all after training, maybe. Maybe, I have no idea actually. This is the sort of thing that I may look at for guessing what parameters I should use in my own model. But isn't that interesting? Doesn't matter that much. Aha! Our May decoder is designed in table A1 and B1. Table A1 varies decoder depth and numbers of transformer blocks. A sufficiently deep decoder is important for linear probing. This can explain why the gap between the pixel reconstruction task and the recognition task. Yeah, this is what I was thinking. I don't know what FT is. Several layers in the autocoder are more specialized for reconstruction, but less relevant for recognition. A reasonably decoder can account for reconstruction specialization, leaving later representations at a more abstract level. This design can yield up to an 8% improvement in linear probing. However, fine-tuning is used. The last layers of the encoder are fine-tuned to adapt to the recognition task. So if I wanted to do my thing where I use where I fix the encoder and interpret its output in several different ways, then we will want to have a deep decoder so that the encoder remains more abstract and doesn't have like pixel representation that we then need to destroy later with our decoding. Interestingly, not made with single block decoder can perform strongly with fine-tuning. Note that a single block transformer is the minimal requirement to propagate information from the visible tokens to the mask tokens. Such a small decoder can further speed up training. In Table 1B, we study the decoder width, the number of channels. We use 52D by default, which performs fine-tuning and linear probing. Narrow decoder also works well with fine-tuning. Yet this just in general seems to suggest that unintelligent decoders work fine if you're fine-tuning, but I'm not planning on fine-tuning. Our default decoder is lightweight. It only has 8 blocks. The reason I'm not planning on fine-tuning and I want to reinterpret the encoder in several different ways at this point is because that way I can use several different kinds of labeled data that potentially preserves it potentially allows me to just find a data set that only has labeled data for, say, head turning, and train on just that, thus get those outputs done really well, and likewise do for other encodings, all from a single complicated encoding thing. But I will have to make sure that the encoding I have contains mostly data I care about and not information about the background. For example, I could do pre-training particularly on faces, or on heads, or at least on humans. Like just isolate the blocks that have the humans in it. Or really test it on the blocks that have the humans in it, because I don't care about the backgrounds. Wall clock time, 15 hours. So that's something I could do, like 15. Now they probably have a smarter computer than mine, because I'm just using my laptop, which happens to have a CUDA capable chip, which means I can do rendering or training on my CPU. But like, I'm happy to train for like 15 hours or like even a week. Maybe. A week might be kind of long. Going out a week, I might be thinking maybe it'd be better if I paid to rent like a GPU somewhere for those hours. The speed up is relative to the entry, whose encoder has mask tokens gray. Decoder width is 512 and the mask ratio is 57%. This entry estimated by trading 10 epochs. Mask token. An important design of Hermé is to skip the mask token encoder and later apply it in the lightweight decoder. T1C studies this design. The encoder uses mask tokens. Skip the mask token. The encoder, yeah, we already talked about this. Encoder uses mask tokens, performs worse. Oh, okay, so this is potentially interesting because, like, the obvious thing is to feed the encoder the mask tokens too, but it actually performs worse in the linear probing. Okay. Encoder. So if we just omit the mask tokens entirely, it only sees real patches, and thus we can improve its accuracy. Moreover, skipping the token in the encoder will greatly reduce trading computation. This leads. Yeah. While clock speed is even faster. Blah 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 blah. Masking sampling strategies determine the pre-task difficulty, influencing the reconstruction quality and the representations. Here each output Hermé is trained the specified strategy: random sampling, middle, clockwise sampling, removes a large portion of random blocks, midwise sampling, that removes 1 in every 4 patches. So there is an actually obvious difference here. Reconstruction target base of pixels without per patch. Results test are with a base of pixels without per patch normalization. Using pixels with normalization improves accuracy. This pre-patch normalization enhances contrast locally. Another variant, we reform PCA in the patch space and use the PCA coefficient 96 here in the target space. Doing so decreases accuracy. Both experiments suggest that high-frequency components are useful in our method. Yeah. For example, detecting different textures. We also can compare a variant that predicts tokens rather than pixels. Target used in feed, specifically for this variant, used the tally pre-trained tally as tokenizer, following by. Here, the decoder predicts token indexes using cross-loss entry loss. So here, so that improves slightly. Slightly reduces a linear program. So tokenization sounds very complicated to me, so I'm not going to do it. Not too surprising. We really wouldn't expect images to have meaningful tokens, would be my guess. Data argumentation. Argumentation. You really can't say words, can you, Shifi? Maybe. Hopefully that gives me maybe a little bit of charm. Maybe. Maybe not. Data augmentation tables. One is studies that influence the data augmentation firm are may pre-training or may works well. Well, pre-training. No, that's not what it says. That's not what it says at all. Or may works well by cropping only augmentation. Either fixed sized or random sized. Both having random flipping. Oh, anyways, data augmentation is when you artificially inflate the size of your data set by doing simple random modifications to it. Like, for example, flipping a bunch of photographs. Or cropping random photographs. Surprisingly, the May behaves decently. You see me? Ah! Insane! The results of my experiment to see if my audience can tolerate what I expect to be boring and, technical and not particularly interesting streams appears to be that you're all really nice and you show up even for the not very good streams, and I really appreciate that. This process is dramatically different from contrastive learning and related methods, which heavily rely on data augmentation. It was observed that using data only augmentation reduces accuracy by 13%. Arboreal simple. In addition, there's no evidence that contrast learning can work without augmentation. Oh, well, I really appreciate that. Though if I do... Two views of an image are the same. Okay, so that's just saying that this is good for classification. We don't really care about that. Mask sampling strategy. Blockwise. Masking proposed in 2 tests to remove large blocks. Our May with blockwise masking tested work reasonably well at 50%. This task is harder than random sampling because the higher training loss is observed. The reconstruction is also blurry. I'm trying to actually comprehend whatever is on screen by visualizing it. Okay, so the thing that's on screen right now, it corresponds to this image. So, to catch fallen entity up, because we have such a small audience, we can catch latecomers up. This is a model that its goal as we train it is that it takes these images with a bunch of blocks missing, and then turns them, and then it tries to reconstruct the image that was originally there before it erased various blocks. This is useful for training a model to vaguely comprehend what kind of stuff to see, that you can then train it to do a particular task. This is called pre-training. It's useful because this way you don't have to have a human label a huge data set. Or at least a comparatively smaller data set. So here they're trying various different sampling strategies to see which ways masking out makes the model perform best. So here we randomly remove 75, here we randomly remove 50 from the center, and here we removed 75 exactly. And they're saying, well, we're about to figure that out. Well, they're saying removing stuff from the center does it works up when you remove it as 50%. The reconstruction blurrial. They also tried grid rise sampling. This is an easier task and has lower training loss. The reconstruction sharper, however the representation quality is lower. And then they conclude, for reasons I don't fully understand, the random sampling works best for May. It allows for a higher masking ratio, which provides a greater speed of benefit while also enjoying good accuracy. Then we talk about the training schedule. 800 epochs. That means that they redid the training data 800 times while training it. So I earlier in the stream speculated that they were using a stop early method, where once you stop seeing significant gains, you stop training it more. Instead, they just made up a number, in this case 300. Main encoder only sees 25 patches per epoch, while contrastive loading epoch sees 200 or even more patches per epoch. Comparison with the previous results on ImageNet. That's just talking about how effective we are. Oh, look! They did. Sorry, that was loud. Look, they did a really good job. They outperformed previous results by a tiny bit. 83.2% to 83.6%, I assume is a percentage. Comparison. Ooh. So in table 3, I'm looking at table 3, so these apparently were all pre-trained in some way. I don't really care about that, because I already know that this method is... Ooh, partial fine-tuning, that's what I might care about, because I'm guessing, that the thing I described where I freeze weights and then reuse them for multiple things is considered partial fine-tuning. The worlds of VITL. By the number of fine-tuned transformer blocks under the default settings from table 1. Fine-tuning 0 blocks is linear probing. Oh, that's kind of similar, but not quite the same. This is talking about how... Yeah, I don't think that's really related that much. I don't fully understand it, though, to be honest. Or your total pre-training time is less than these other models. I don't really care about that though. This is comparing supervised pre-training. Oh, that seems way less interesting. Whilst my voice is giving out, perhaps because I wasn't particularly responsible and leaned back and then just yelled loudly to get my voice to pick up on the microphone, I should try to speak more quietly, you see, because speaking quietly is both easier on your voice when you're speaking for long periods of time. It often sounds better. Linear probing. I really need to learn what linear probing is. I think it means just running the model and seeing what the results are. Fine-tuning is something else? I honestly don't know, though. Linear probing has been popular protocol in the past. Wait, maybe linear probing is just when you add another layer that's linear on the top, and then like measure various stuff in it and see what you extract. For example, I might be doing linear probing. If that's what linear probing is, and I have no idea if that's the case, linear probing might be what I want to do. Or I'm planning to do, or at least the first thing I should try to extract various weights. Or extract the complicated analysis of the person into the weights I care about. I'm guessing because they're talking about freezing here. So that means this is actually super relevant, perhaps. Maybe. So they're... I think what they're doing is that instead of like trying to replace the decoder with something else, they are freezing everything but the last layers of the decoder, which include deep layers here. Oh wait, for the sake of fallen entity, if they're still paying attention, this is the model of the model. This is a diagram of the architecture. Hello, MP. Oh, everyone's coming by. Mwah, mwah, I appreciate it. So, this is the model of the paper we're reading about. So I think what they're doing, when they're comparing the various pre-trainings, is we have the full encoder and decoder all up, but they're pre-training the decoder to do a different task. Or maybe not to do a different task, but specifically on the trained data. Honestly, if we could make vtuber models also react to voice, like if they could pick up the emotion in the voice. Yes, I'm streaming very early today. This is because lately I've been feeling full of energy. I felt so much energy in the mornings, and thus I felt enough energy to just ignore the part of me that was saying, oh, the stream is terrible, and like, I'm going to like feel so anxious that I won't get anything done. I'll just like stare at the stream, nothing done. I was brave enough to think, even if it's just a stream for half an hour, I'm going to do it anyway. Also look at almost 2 hours. That's not a short stream. Where were we? We're at false fine-tuning. So I think what this is... This is how effective it is on the reconstruction task. Wait, maybe the classification task? Exclusively, like reusing The decoder. Or maybe the encoder gets more. I'm kind of confused, to be honest. Maybe the encoder gets more layers. Wait, great to hear. You should be careful not to drink too much energy drink. It's bad for health. This is true. I have turned to. Luckily, all of my methods are doctor approved. So you don't need to worry about my health. Also, another thing I've done is I've prepared several different kinds of streams I might do in YouTube, and thus I can more quickly stream without thinking, oh, I want to stream Hollow Knight, but then I have to undo all the work I did to set up this stream. Also, because energy drinks work primarily on caffeine, and caffeine suffers from tolerance effects, taking energy drinks every day is not going to be particularly effective. Also, energy drinks can just have the problem of normal sodas. Fine-tuning only one transformer block. So if these are encoders, so this suggests that I will suffer some accuracy problems by not doing any fine-tuning. No, streaming on Linux is not necessary. You shouldn't blame all these problems on Linux. I make things harder on myself several ways. I could make things easier on myself in other ways too. I suspect the crashes we were having that other stream, I think that happened because I updated my computer without restarting it. And unlike Windows, which forces you to restart every time you update Windows, Linux doesn't force you to do this. Instead, random things just start crashing, and I suspect that's what I did. Because I tend not to restart my computer for weeks on end, and this is bad if I update my computer in those times. Also, I use a distribution of Linux which has all the latest software, but doesn't prioritize stability as much, and thus it's more likely to just randomly break on an update. Also, I refuse to use the easy way of doing things. I mean, you start using Linux, in my opinion, not because you think, I want less arbitrary problems. You start doing it either because the software you want to use best supports Linux, or you do it because Windows has features that you actively dislike, like advertisements, or forcing you to log in, or poor integrations with missing Unix features that you can get around that with Linux subsystem for Windows, where you run a little tiny Linux distribution on Windows. But yeah, I just make myself. I make plenty of problems for myself. So only some of them you should blame Linux for. I mean, the fact that I use. Yeah, Windows has ads. For example, I think I haven't used Windows in some years by now, but like back in the Windows 10 or Windows 7 era, I forget when, they had like Candy Crush pre-installed on Windows. By default, as like this gigantic icon in the start menu. But also like advertising other Microsoft services, like pushing you towards using Microsoft Outlook, or lately they've been forcing you to log into Microsoft's cloud services. They like push their Azure backup services. They definitely push Edge really hard. Sometimes, so like when I have problems, they're problems that I made myself, I feel less bad than if they're problems that some company did to me. This is not necessarily the most productive thing. Also, random things will bother me. For example, I'm using the distribution supplied copy of OBS. This means that OBS doesn't have a web browser embedded because the guy who packages it for real the only ads I see are when I use their services without the subs. And they get mad. Not stopping me though. Oh yeah! Like AdBlock works. You can set up AdBlock. There's lots of ways to make Windows more tolerable. The question though is if you want to. Also, I make problems worse for myself by not wanting to spend any money and also being unreasonably careful about doxing. So fine-tuning with at least one transformer block seems to help significantly. Suggests that I should put transformer block in my fine-tuning to make the models work by extracting various properties from them. Transfer loading experiments. Here they try object detection, segmentation. Pixel-based math as well. I hear we're talking about tokens versus pixels again, but we already did that. I don't really care though. I wonder what the B's stand for. Maybe big, large, and huge. Oh, also you can buy into the macOS world. If you're fine with doing things the macOS way, that can work. Discussion conclusion. Just like in high school. Or so I've heard. I am not with the Mafia. As far as I know. But I have like a... So what it is that like all VTubers, I'd rather not get doxxed. I'd rather have control over my image. I don't want my VTuber activities to affect my future job prospects if I have to go out into the world and get like a normal job. If I post cringe political opinions somewhere else on the internet, I don't want to get those attached to my VTuber identity because I'd rather not engage in the discourse. But normal people will use normal measures to avoid this. Like just not officially saying what their AO3 handle is, and thus people can't find their AO3 their AO3 fanfics from when they're 13. I have a tendency to think about what if someone was applying maximum resources towards trying to find me? Oh, what if they look at my AO3 fanfics and notice that I type with a similar verbiage as when I type tweets? And thus I'll think, oh, therefore I need to make sure when I type tweets, at Shifi, but that's who I truly am, to be clear, because fiction always is true. Never am I actually just a normal person. This is just a thing I've made up to fit in with the other VTubers, you see, because they are all also pretending to be real people. No comment on if I have an AO3 account. I'm just talking about how, the reason I am extra careful about getting doxxed is more moraphobia psychological reasons. But where I am more careful than what I can tell other VTubers are doing. But I'm not convinced that this is justified. Partly because lots of the big VTubers, I forget her reincarnation name, but there was the Hololive Gargura who apparently got doxxed, and yet most VTuber fans are polite and don't try to go chase up her real world identity, though people will share her pre-VTuber identity where she was doing similar stuff. But so even if it's technically possible, by chaining through a long series of connections to dox me, it might be still okay. But also, I don't want people from my real life being able to show up to my streams, because that'd be embarrassing and stressful. Because then if I do something cringe, they might say, when I see them next time in real life, they might be saying, that was cringe when you streamed that. You seem to be using years of your life on this. Yeah, fair. I've been purposely trying to be more casual about it. You are correct. I Air MP, you have correctly identified a problem I have. I mean, in truth, I trust you 5 people who watch, so if I do leak a little bit, I can just delete the VOD, and it's highly unlikely that any of you guys are waiting and practicing. I've learned the name of the folder which keeps a project in, so I'm going to now scour the internet to see if someone else has the same name of folder, etc, etc. Okay. Oh, that's the end of the paper. So the truth is my voice is giving out. So I'm gonna need to stop stream. Plus I have later stuff that I have to get to. So we're actually going to be, heading out. I have a short that I have like 11-second long. My hairs are supposed to be white. Oh, unless you're just like suggesting that I'm like aging and like not fully, and like I'll never achieve my dream of being a VTuber because the inevitable march of death. I mean, fair. Though my primary obstacle to being a VTuber is just being brave enough to press the start stream button rather than all this other stuff. Because like lots of streamers stream like the same thing all the time rather than thinking of unique, clever streams. Or even weird streams like this. Sorry, was I too grisly? Anyways. Thank you for joining my stream. I was gonna say, oh right! I have an 11-second long Halloween song that's scheduled, that is like already done and uploaded, and it will be released on YouTube and TikTok as a short, next week sometime, so you can look forward to that. Turn my hair to be white. No, that's not a French thing. That's definitely like a thing that I know of. I just entirely failed the comprehension check. No, that's a normal reference. I'm just not smart. Bye-bye.